and good morning, everyone. Okay, so an official good morning to all of you. I hope you enjoyed your week so far. And I will start now our last lecture on gravitational waves. And my plan for today is to talk a little bit about gravitational wave energy emission and energy fluxes, which would lead us to the luminosity, so quadrupole formula for luminosity. I would talk a little bit about radiation reaction effects. And then in the second half of the lecture, I will try to give you a very brief overview on like key concepts in numerical relativity. And I think, as we discussed yesterday, since it's going to be quite brief, if you have any further questions or if you want to go into any more detail, we can use the Q&A session to do so. Okay. And as usual, if you do have any questions, just interrupt me or post your question in the chat, and then we can go to that. So without further ado, let me just switch to my notes, to my notebook here, and start. Oh, and while I'm setting up, are there any questions about yesterday or the last few lectures that you would like me to address before actually starting with today? So that doesn't seem to be the case. So let me just get started. Today is the 25th of June. And we want to talk about energy momentum and gravitational wave energy emission. Okay. And the first question that we have to answer, of course, is how would we define the energy of our gravitational field? Because we don't really have a local measure of our gravitational field. Remember, we needed to have at least two nearby particles that would allow us to measure the difference between in proper distance between those particles. So what we will do, the strategy that we will adopt in this still weak field approximation, is that we continue to treat the perturbation associated to the gravitational wave as an independent tensor field propagating in our flat space-time. And then we will calculate the stress energy tensor that is associated to that metric perturbation. Now, as a side note, a little bit as a guide of where we need to go and to guide our calculation, let's think about the energy momentum tensor for a scalar field or for an electromagnetic field. In this case, we know that the energy momentum tensor essentially scales, for example, like the gradient of the scalar field squared, or the gradient of the vector potential squared. And that seems to indicate that we may end up with a description that involves derivatives of this metric perturbation squared. What that means for us for the calculation is that we need to extend beyond this first order approximation that we've used so far, and that we actually have to expand our metric up to second order. Now, let me talk you very briefly, very sketchy through that calculation so that we can end up with a description for an energy momentum tensor for the gravitational field, because that forms the basis to then be able to compute energy fluxes and effects due to the radiation of gravitational waves. Okay, so with all that said, let me just sketch the second order perturbation theory for the metric. As I said, here we will need second order expansion of the metric. That is, let me use the following notation. We will say that our metric d mu nu, again, we will expand around flat space or around flat space-time, described by the Minkowski metric eta mu nu plus epsilon. Let's keep h mu nu for the first order perturbation, and let me write epsilon squared h mu nu with this little 2 over here to indicate the second order perturbation. Okay, So similarly, if we look at the curvature, and this is what we will need, we can expand the Ricci tensor, well, formally in something that looks like the zeroth order Ricci tensor plus first order, this is almost trivial, oops, plus epsilon squared second order. So let's schematically at least identify how these different contributions look like. So for that, let's just write down the Ricci tensor explicitly in terms of our Christoffels. I know you're probably all familiar with this expression, but for the sake of the argument, let me just write this out once. So mu rho here plus, and then we have Christoffel rho sigma, Christoffel sigma mu nu minus gamma rho mu sigma gamma, oops, sigma rho nu. Okay, so if we expand that, and let me be very schematic, I'm not going to use any indices, I'm only interested in the order by order expansion that we have here. So very schematically, what we would get if we expand that out, remember how we compute the Christoffel symbols, then the first term that we would get would be a second derivative of the background metric, so that would vanish, obviously. We would have a first order contribution of second derivative of our first order perturbation plus epsilon squared second derivative of our second order perturbation. And then from these last two terms, you would have combinations of this form derivative of background metric squared, which of course, again, vanishes, plus, and then the first order contribution would be of this form, which involves a partial derivative of the background metric also vanishes, plus epsilon squared. And here we would have the partial derivative of our first order perturbation, but squared. So now if we think about the Ricci tensor as a derivative operator, I can actually write out the different components in the following form. So that I say at order epsilon 0, our zeroth order Ricci tensor, which I could write in this form, Ricci tensor, the operator constructed with the background metric, acting on the background metric is 0, as we've already seen. Could think about the first, oops, just get this out of our way, the first order correction, R mu nu 1, could be written as Ricci tensor as operator constructed with our background metric acting on our first order perturbation. The other combination we already saw vanishes, so this is 0, which means that if we insert that into our Einstein's equations, and let me also reintroduce the matter energy momentum tensor, it gives us exactly the wave equation that we have already seen in our lectures. So box operator acting on our gravitational potential, h mu nu, would now be minus 16 pi T mu nu matter. And I'm suspecting that I actually may have a factor wrong here. So let me check this afterwards, but conceptually it's clear what's happening here. So we have our wave equation for the metric perturbation sourced by just a matter term. Okay, and then at second order, what we would have here, R mu nu, would be given by the Ricci constructed with our background metric acting on our second order perturbation, plus the Ricci tensor constructed with our first order perturbation acting on our first order perturbation, and then the last term that we would get here is acting on the background metric, and that again would be 0. So if you look at this more carefully and compare to the schematic expansion that we have above, then you see that this first term here is essentially a linear operator and gives us the wave equation. So if I write this out, this would be nothing but 1 minus 1/2 wave operator constructed with a background metric acting on our second order perturbation. And then the second term here captures all of the nonlinear terms that behave as first derivative of our metric perturbation squared. Okay, good. So terms and schematically, that would be the leading order here in this operator. Now, I'm not going to write out this operator. You can look at standard textbooks to do so. Let me just continue conceptually so that we so what I will do now is basically look at Einstein's equations at second order in the expansion. And that will allow us to define an effective energy momentum tensor in terms of the quantities that we've written down here. And in the end, I will give you an expression for this effective energy momentum tensor in terms of the metric without going through all the detailed sub-steps, because that's not very illuminating and you can follow at home. But let's continue with what I just said. So I'm not going to write out the second term explicitly as it's quite lengthy, but conceptually what we would do now, so the strategy is that we say, okay, insert all of this in Einstein's equations at second order. Then let's rewrite the equations that we get as essentially something that looks like the Einstein tensor operating on our second order metric with some energy momentum tensor. And this you will see in a moment. Yeah, with some effective, let me just already suggestively call that T mu nu. So in forms, you will see this becomes the Einstein tensor or Einstein operator constructed with our background metric, acting on our second order perturbation equals 8 pi, and then this new T mu nu that I introduced here. And if you go through the mass, you see that this T mu nu can be written as, well, 1 over 8 pi is just a prefactor, and then the Ricci tensor or Ricci tensor operator constructed with our first order perturbation acting on our first order perturbation minus 1/2 eta mu nu, and then the trace of this operator. Okay. H and kappa lambda here for the trace. And this energy momentum tensor or pseudotensor, I should be saying, is actually well known. So this T mu nu is a Landau-Lifshitz pseudotensor that describes the energy momentum of the gravitational field. Okay, good. So some of its properties, I'm not going to write those down. It's a symmetric tensor, and is well, I think what's important to note here, if we were to write this out, we will see that it's indeed quadratic in first derivatives of our metric perturbation. So precisely what we already expected or suspected from comparing to the energy momentum tensors for scalar fields or vector fields. Okay, one more note. So I wrote here pseudotensor, and the reason is that this energy moment, or this T mu nu here, is actually not gauge invariant, so it does not satisfy the transformation rules for a tensor, and you can check that at home. But if we average over several wavelengths, then the averaged quantity is actually or can be shown to be gauge invariant. Yeah, so maybe that as a last note. So this is not gauge invariant. But we can make it so. By averaging over several wavelengths. Okay, good. And again, we can now try to calculate how this energy momentum tensor looks like explicitly. So essentially solving the equation here. Again, let me just give you the final results. So what we would do strategically now is to actually work in the transverse traceless gauge, which is simpler, and one can show that then the final result that we get after all the averaging is actually also gauge invariant. Yeah, so we are working in the transverse traceless gauge that we have seen in the second lecture. We will average, we will use partial integration repeatedly to essentially find terms that are divergences so that they vanish. And then if we do all of that, oops, let me just go to the next page. So after all that, we will arrive at the following expression that our Landau-Lifshitz pseudotensor is given by 1 over 32 pi, and here we are averaging, and we find a rather simple expression, which is the partial derivative mu h rho sigma in the transverse traceless gauge still, and partial nu h, now upper indices rho sigma in the transverse traceless gauge. So this is our final expression here for this energy momentum pseudotensor. And since that describes the energy of the gravitational field, we can now use this tensor to try and define or talk about an energy flux and the luminosity of gravitational waves. Before I go there, let me just ask if you have any questions. Okay, that doesn't seem to be the case. So let me just continue with the next section on energy.
Excuse me, can I ask a question?
Yeah, sure.
So you mentioned that in order to make this T mu nu gauge invariant, you have to average over wavelengths. Where did that wavelength come from?
So in the simplest case, think about, well, your gravitational wave does have a wavelength, right? So think about basically just taking enough of your signal that you can average over. So just so instead of having a monochromatic signal, average over a few wavelengths here.
Oh, okay, so this T mu nu is not, you cannot make it gauge invariant off shell. You have to impose the gravitational wave solution and then make it gauge invariant.
Oh, that's a good question. So this is certainly the context that I'm thinking about here. Yeah.
So it's not gauge invariant.
Yeah. So not in general. So if you, so I didn't write down this T mu nu explicitly, but wait a second. If I go back, let me just go back up, right? So the more general expression we have here. Sorry, I'm not sure whether you can see my pointer. So this would be the general expression, right? That you could compute, and this is not gauge invariant. And now we say, okay, we have as application in mind that we are looking at gravitational wave solutions that we know have a spectrum, frequency spectrum, and associated wavelengths. So let's try to average over those wavelengths. Yeah? Okay. Do we have any other questions? Okay, so I don't see any. Okay, very good. So let's now talk about the energy flux and gravitational wave luminosity. That is the goal that we have in mind now, is to derive, and again, in our weak field approximation, so derive essentially something like a quadrupole formula for the luminosity. For luminosity LGW, so luminosity of our gravitational wave, which is associated to the gravitational wave energy flux, like so. Okay, so that's where we want to go. And again, let's just draw a sketch of what our situation is here. So we've seen that several times now. So we have our source here. We have our observer somewhere sitting here. There's some radial distance. And now we want to measure the flux arriving at our observer. So in other words, if we were to draw a circle around our source, we would want to measure the flux on this sphere here. Okay, so, okay, yeah, and let me just write it like so. So we measure the flux on a sphere. And in particular, we send the sphere to be at spatial infinity. Yeah, that's what I mean by this notation here. We also introduce a normal vector n mu, which in this drawing here, if we say this is our radial direction, our normal vector would point this way, and in adapted coordinates would be aligned with radial direction. Yeah, so this is a unit. Okay, space-like unit normal vector. And it's normal to the sphere that we just introduced. And normalized like so. And is aligned, as I said, with a radial basis vector. Okay, so first thing we need to do is compute the energy flux through that surface at infinity. So what we would have is that the flux, and let me just to be short, introduce the dot as being the time derivative. So again, we will have something dot being a time derivative, and I will use the prime for some radial derivative. Okay, so now the energy flux here would be given by an integral of our energy momentum tensor that we've computed before, mu 0, contracted with this normal vector, and then integrated over our sphere. And we can write that as, if we write that out, yeah, in the limit that the radius goes to infinity, integral over integral of T0R, so that's the contraction, and then R squared, the omega. And if we now insert the formula that we've just derived up here, so if we use the one from the previous section, we can write this as 1 over 32 pi, limit that R goes to infinity, integral, and then we have here, writing everything out, the time derivative, so H dot, rho sigma in the TT gauge, times the radial derivative, so H prime, rho sigma, again in the TT gauge, averaged over R squared, d omega. Oops, let me just separate this a little bit. Okay, so this is the general expression for our energy, and now we can apply the quadrupole formula that we have seen yesterday to actually derive explicitly what the energy flux is in terms of this quadrupole formula. And again, I will not go through many of the details, but just some of the key concepts that I think you need to know. In particular, say, strategy is to use a quadruple formula. Then we introduce the reduced quadruple moment, which is nothing else but the trace-free version of the quadruple moment. Oops. That is, you introduce something that I call Q, which is ij minus 1/3 delta ij delta kl ikl. So this is a trace-free part, spatial trace-free part of our quadruple moment. We will need the derivatives of hij. Yeah. And again, let me just write out the final result. So the first one, of course, is obvious. The time derivative just gives us 2/3. And then the third time derivative of our reduced quadruple moment. And the radial derivative we can show using that we are working or looking at the quadruple moment in the retarded time. We can show that this becomes minus 2/r. Again, the third time derivative of the quadruple moment. Oops. Ct. And then there are terms of the order 1/r to the 1/r squared that we neglect because we are in the far field. So they will be subleading here. Okay, so now we can take all of this and insert in the flux. And we would arrive at the, yeah. Okay, so let me insert this here. You're not quite done yet. There's one more step that we need to do, and then we are done. So here we have minus 1/8 pi, limit that r goes to infinity, integral d omega, and then we have the third time derivative here of our reduced quadruple moment times third time derivative qij here. Still in the transverse traceless gauge. So the final step that we would have to do is to transform back to not be in that gauge. And I'm not going to do the details. I'm giving you the final formula for that, just for you to know that this is the final step that we would have to do. Yeah, so if we do this transformation, okay, yeah, we would arrive at what we call the quadruple formula for the gravitational wave luminosity. So this would give us the luminosity that is E dot for gravitational waves, and this is given by minus 1/5. Now let me reinstate our natural constants. So minus 1/5 Newton's constant divided by the speed of light to the fifth, and then we average over here qij third time derivative, and now without the transverse traceless gauge, qij again third time derivative without the transverse traceless gauge, and that is our quadruple formula for gravitational wave luminosity.
Excuse me, can I ask you?
What is that additional, can you repeat what is that additional term to Hij prime and why it doesn't appear in the in the flux?
Okay, so this, okay, let me just finish writing the sentence and then I can explain what we have up here. Okay, so in our expression for H prime, I've skipped several steps. So if you take the derivative, you use the fact that we are working with a retarded time. And then what you find is one term that I've written out here, which is this -2/r third time derivative. And then you get a second term that scales like 1 over distance squared. And remember, we are interested in the far field, we're far away from the source. So for very large distances, that is the term that goes like 1 over distance squared is completely subleading. So we neglect that term. Yeah, so this curly thing, let me just write this. So this is supposed to be an order operator. Yeah, so we neglect this last term here so that we only have those two contributions from the third time derivative. Okay, very good. Now, let me give you the results for the example of a binary system. So the parameters and all the settings will be exactly the same as what we had yesterday. So we will just continue with the examples that we've already looked at and look at what the gravitational wave energy flux looks like. And let me just continue on the next slide to do this. So let's look at the example of a binary system. And if we take the quadrupole momentum that we've already looked at, compute the reduced quadrupole moment, and insert everything in our quadrupole formula for the luminosity, we end up with the following expression, or following two expressions. So we can write the energy flux as minus, the coefficient here, minus 32 divided by 5, some coefficients pi over 10 to the 3, they are not important, so these are just coefficients. Then we have the Newton's constant, over 7 to the 3 divided by speed of light to the 5th. And here we have again our chirp mass that we introduced yesterday, to the power of 10 over 3 times the gravitational wave frequency to the power of 10 to the 3. So just to remind you, so this curly m was a chirp mass, and it was defined as m1 and to the third, m2 to the third. So that was our component mass is divided by total mass to the power of 1 over 5. Okay. Now I want to give you one more formula that I think is also quite neat, and I tend to use quite a bit, especially in outreach talks. So here you can also get a very nice scaling with your system if you rewrite your chirp mass in terms of what we call the symmetric mass ratio, and I will introduce what that is in a second. So if you do that, you can write the energy flux as this coefficient, speed of light to the 5th divided by g Newton, this symmetric mass ratio that we also call eta, times the velocity of your system divided by the velocity of light to the 10th. And here I've introduced the symmetric mass ratio. And this eta is given by m1 times m2 divided by total mass squared. Okay, so with all of that said, let's put in some numbers. So if we remind ourselves of the Hulse-Taylor pulsar that we talked about yesterday, then the gravitational wave luminosity associated to it would be minus roughly 6.5 times 10 to the 23 watts. And that's a system that's still very early in its in-spiral and just slowly losing energy in the form of gravitational waves. So it's emitting this gravitational wave energy. And as a consequence, these orbits shrink, as we have seen and discussed already yesterday. Okay, good. So that's it. So we have now discussed losses of a binary system in terms of gravitational wave energy. What I haven't told you is that likewise gravitational waves carry angular momentum. So your system will also lose angular momentum such that in the end of the day, you have two effects. First of all, the size of your orbit shrinks. So this is what we have already seen and verified with this first observation of the Hulse-Taylor pulsar, but it also decreases eccentricity. So imagine your binary two stars or two black holes forms, and in the beginning they may still be quite eccentric. I'm not sure whether you can see that very well, but due to the emission of gravitational waves that carry away angular momentum, your binary will actually start circularizing. So by the time that they enter the LIGO sensitivity band, most of our black hole binaries or neutron star binaries will actually follow really kind of circular or quasi-circular orbits. Okay, now the decrease of the orbit is the last bit that I wanted to tell you a little bit about, which is a reaction of the system onto the radiation. And just to give you an idea of how the orbits, the orbital period, and ultimately the gravitational wave frequency changes over time due to the emission of gravitational waves. And that's the last bit that I want to tell you before I move on to numerical relativity, because I think that really gives you the main feature of what a gravitational wave looks like as a function of time. Okay, so with all of that, let's look at the final part here. So section 5.3. Radiation reaction, and I should say I will still stay within our weak field approximation perturbation around flat space. So these are like the lowest order terms that you can think of, for example, if in a post-Newtonian expansion. So that's the basic features which are important for us to understand what's going on. So radiation reaction. For binary. And sorry, let me just be more specific. I will focus again on an already circularized binary. Okay, so what we will use here is essentially energy balance equations where we equate the energy flux or change in orbital energy. Let me write this as E orbit, the change in the orbital energy equals to the change in the gravitational wave energy. And if you look at our equations, you see that this is already has a negative sign. That is, energy is carried away from the system. By gravitational waves. Good. And as I said, we will actually stay within the Newtonian approximation here, so we can write the orbital energy as the following. E orbit is nothing else but minus Newton's constant, the masses of our two components, and divided by this separation L0. Good. So if we insert that in the balance law, we can study what the change in the orbital separation is. So that's the first bit. And here I'm just writing down the differential equation that we will find. So what we would find is that the change in the separation, so dl0 by dt, equals minus 32 divided by 5, Newton's constant to the third, speed of light to the fifth. And let me write this equation in terms of the chirp mass. So we will have the total mass m to some power, and the chirp mass curly m to the power of 5/3, and then we have the separation to the power of -3. Okay, I'm not going to solve this, but what I will write down for you is both the change in the orbital period and the change in gravitational wave frequency. So can again start from your energy balance law, and then you find change in orbital period would be dp. Let me call the period p, so it's d capital P by dt, and that is again some coefficients here. To the 3, Newton's constant to the power of 5/3, speed of light to the fifth. I'm writing it again in terms of the chirp mass, now to the power of 5/3. And then we have the period to the power of -5/3. So if you solve this equation, you find that the period as a function of time goes like minus, and then again, I'm just writing out the coefficients here. To 8, and then the important dependencies here are Newton's constant times chirp mass to the power of 5/8 divided by c to the 15/8, and then the dependence on time comes with a power of 3/8. And the minus sign indicates that your period actually decreases over time. And this is exactly what had been observed for the Hertz-Taylor pulsar. Remember, we have seen this several times now, where we looked at the orbital period shift as a function of time, which decreased. And the observation are in excellent agreement with the predictions actually by the quadrupole formula in general relativity. Okay, now the last, or let me just wait for a moment and then come to the last bit where we look at the change in the gravitational wave frequency and actually look at the morphology of a typical gravitational wave signal coming from a binary. Okay. Good, so let me just continue on the next slide. So the change in gravitational wave frequency, we label that as FGW. And again, inserting in the balance law will give you this differential equation here, dF by dt is given by a coefficient times Newton's constant times the chirp mass to the power of 5/3 divided by the speed of light to the fifth. And then we have here the frequency as a function of time to the power of 11 over 3. And yesterday we had this question why the chirp mass and why we can measure this so accurately. If you look at this formula, what we can do now is, so not in the merger, but in the, if we have a system that has a very long in-spiral, we can very accurately measure both the frequency at a time, or at least an interval of time, and the change of that frequency. And if we have those two quantities, we can insert that in this formula and actually estimate the chirp mass, so this particular combination of the component masses and the total mass of the system. Yeah, and that's why for the in-spiral, we can get very, very accurately the chirp mass. Okay, now if we look at the, if we solve this equation, then the evolution of the frequency, the gravitational wave frequency, will take the following form. Again, there will be some coefficients that I'm not going to write out. And then we have the speed of light to 15/8. Now we have Newton's constant times chirp mass to the power of -5/8. And then we would actually get time to the power of -3/8. I think there should actually be a minus sign here. Okay, so this is how the frequency of a gravitational wave evolves as a function of time, at least in the early in-spiral stages. So if I sketch that, we actually will go now towards a similar plot that we've already seen yesterday. So let me plot here the gravitational wave strain or amplitude as a function of time. Now, if we just plot the envelope of the frequency evolution, it would go like something like this. So it would increase, so the amplitude would increase in time, but also the frequency itself would increase in time. And I'm not a very good artist here, so this should be like a really nice sinusoidal signal that increases in frequency and amplitude. So that kind of behavior in time gives you a chirping-like signal. So it would do something like whoop. Yeah, so this is what you should hear. And because of this morphology, which is very similar to the chirp of birds, this had actually been labeled a chirp signal. Yeah, so this is essentially how the gravitational wave would look like, that is emitted by an in-spiraling binary system. So here we are in this stage where we have two compact objects, say two black holes or neutron stars, that are in-spiraling around each other, still sufficiently or relatively far away. And here, the description that we have for this part would be a refinement of what we have looked at in these parts of the lecture. So this part would be described by what we call post-Newtonian series. This is essentially assuming weak fields, slow motion, and essentially an expansion in powers of VOSC. Okay, so this is a good description if our two bodies are very far apart. As they emit gravitational waves, we've just seen the frequency increases. We also know that the frequency is directly related to the orbital frequency. So that means that through gravitational wave emission, our orbits start shrinking. And if our two objects are sufficiently close, then all this weak field approximation breaks down, because now we are talking about, strong gravitational fields. So very close to the merger, and through the merger, we really have to solve Einstein's equations in full. So if I continue this drawing here, we would go through this phase where we have the merger. So this is our highest frequency and amplitude. And then after the merger, so oops, let me have my drawing down here to not overlap with the equation, but here you would have this scenario where your black hole or your compact objects essentially touch and form a final rotating object that emits gravitational waves and is a highly distorted rotating object and emits gravitational waves that gets rid of all the non-axisymmetric modes in our system. So we have, if our final black object is a black hole, we would have, after the merger, essentially a ring down phase where the signal decreases exponentially in time. Here, so this would be, okay, the ring down. So our final state here would be a single rotating object, or in this case, a single rotating black hole with some spin around its axis. So in terms of descriptions, so I've already written down the post-Newtonian part for the in-spiral. This is the merger part, and here we really need numerical relativity because we have to solve Einstein's equations in full. And as I said, I will take the last few rest of the time today to talk about this. And then these final stages here, this ring down, can be described in two ways. So we kind of naturally capture this with numerical relativity because our simulations would start a few orbits before the our black holes or neutron stars merge, would go through the merger and then cover this ring down part as well. So this is captured by numerical relativity. Oops. But in this part, you can also think of this final, or to describe the ring down of the gravitational waves, you can also think about this as a single rotating black hole with some perturbation. So you can actually, in this final stage, also use perturbation theory, that your background space-time now is not flat space, but you would perturb around a single black hole space-time. So here you would use perturbation theory. So if you're familiar with quasi-normal mode calculations in whatever context, this is essentially what you would also do here. Yeah, so if you want to look this up, you would have the Regge-Wheeler, the Rayleigh equations for a non-rotating black hole. You would solve the Tucholsky equation for a rotating black hole. And of course, in terms of perturbation theory, there has been a lot of work in other, for example, high-dimensional spacetimes or asymptotically ADS spacetimes as well, which of course are not relevant here, but have also been done. Okay, good. So with that, I would stop here, take any questions that you may have before I actually move on and talk a little bit more about this middle part here, numerical relativity.
So I had just a basic question. So last lecture, we wrote down a formula for the strain H naught as a function of the chirp mass and the frequency, but also R, the distance of the gravitational wave. Mm-hmm. And it was, you know, so and now we have a formula for so now we just have a relation between the frequency and the chirp mass. So if we can just measure the frequency as a function of time, that's how we get the chirp mass, and then we can go back into that previous formula to get the distance. Is that the right way to think about it?
Exactly, okay. Exactly. Yeah, because the information that we get is essentially a signal that I have drawn here, not very well because I'm not a very good artist, but that's exactly what you can do. Yeah, because we do get the amplitude evolution also from the signal. And as you just said, this is directly related also to the distance. Yeah. Okay, so Jonathan is asking in the chat, how can we get the final or radiated mass from the signal? So for this final bit, so the merger and the ring down, there are actually two ways of getting this information. So one, and this is what has been used predominantly, is really comparing the signals that we get to our numerical relativity simulations, where we would get the total mass of our final object. And then the energy can be related again to the strain and frequency. What did I want to say? Okay, I think I lost myself. Oh, so one more thing that you can do in theory is the following, that if you have this ring down, if you calculate the frequencies of this ring down perturbatively, you can actually identify the real and imaginary part of this ring down frequency. So the signal that rings down here has a very characteristic frequency that is directly related to the mass and the spin of the final black hole. So if you can measure the ring down frequency accurately, we can also infer the mass and spin of the black hole, of the final black hole that has formed. Yeah, so in some sense you would get information about your initial stages, or at least a combination of your initial components from the in-spiral quite accurately, and then through comparison to numerical relativity, or in an ideal world, if you could see the ring down through comparison to a perturbation theory, you would get the final mass of your object. Okay, good. I guess that answers your question. Do we have any other questions here?
Yes. When you, in the in-spiral phase, talking that you then do a post-Newtonian expansion, both in weak field and in V over C. But at least for our calculation, it seems like we didn't have to do a V over C expansion. So it seems like we have expanded in powers of H, but not in powers of V over C.
Well,
then for the higher orders, do we need to expand in powers? Not really.
So we have implicitly, because we have assumed that our velocities are small. Right, so from the beginning, we have worked in a framework where we assumed slow motion. So in some sense, think of what we have done as like the zeros order in an expansion in V over C. Right?
Okay.
Yeah.
So where did that approximation go into? To the energy momentum tensor, or to the wave equation for H mu nu?
Yeah, so that went in the beginning already. Yeah. I mean, we still, so okay, so the equations that we've got do have this power. If you were to rewrite them, would have a power of V over C in them, and that would be like the lowest order that you would get for, say, your radiated energy. Right, and then if you expand further, if you say, okay, let me go a little bit away from my slow motion approximation, let me expand in V over C, then you would essentially get what we have as with the V over C power that we have in there as a leading order, and then we would get higher order corrections to that.
Okay, so it is really a double expansion, and then the work is expanding in both directions, both for high powers of H and high powers of V over C.
Yeah, and I mean, in some sense, if you think about slow motion, that would also reflect essentially you could rewrite that in an approximation on your orbital frequencies, for example. Right. Okay. So we are basically looking at systems that are very slowly moving, that are still very far apart from each other and slowly moving.
Is there any connection between the two approximations? As in, can we expand to any order in H and any order in V over C independently, or do we need to be careful about the order of limits?
Yeah, so you would get H in terms of higher powers of V over C, right?
So they are tied. They are not just typically independent parameters.
Okay. Yeah. So you would express your strain, for example, or gravitational wave amplitude in powers of V over C. So you have the leading power that we've got, and then you would have higher orders thereof. Yeah,
Okay.
and that if you want to look this up, that goes under post-Newtonian expansion.
Okay, thank you.
Yeah. Yeah, and then, I mean, other effects that we've completely neglected here is what if our objects are spinning? So that would come in at a higher order in this V over C expansion, for example, right?
That makes
Or,
sense. Thank you.
yeah. Okay, do we have any other questions?
Yes, you might have already answered this, but if I were to include, if I were to study, the internal structure of the neutron stars, for example, in this, using this gravitational wave data, where does that input go in?
Okay, so that would come in. So when we started studying this example of a binary, remember we made an assumption that we are using point particles. So we've described our energy momentum tensor, the T00 that we talked about yesterday. There we assumed to have point particles. So that would be modified if we had finite size effects.
Okay.
Yeah. And then consequently, of course, everything that we talked about today for the example of the binary. Do we have any other questions? Okay, so if not, and looking at the time, which means I have about 10 minutes according to my clock, I would start talking about really basics of numerical relativity, and maybe given the time, just the main ingredients that we need. And again, so this maybe we can I can get feedback from you what you would be more interested in, but I don't think I have much time to actually go through the formalism that we have. So this is something that if you're interested, we could do in the Q&A session. So Thomas, would that work for you? So basically looking at the organizers, if they would be okay with that, and looking at the students, if they would be interested.
Yeah, I mean, it has the disadvantage that we'll probably have to split. So only the students,
Right.
well, some of the students that are interested. But yeah, I mean,
because I mean, essentially one of the basic things is like the ADM formulation, which in 5 minutes right. would be a challenge, and I would probably lose some of you, but I can mention that. Right. Yeah, would that be okay with everyone?
Yeah, I mean, you can take an extra 5 minutes too if you need it. I think that's fine.
Okay, then let's do that. Good. So with that, I will just go through let's just go to the next slide here. And very briefly, like I think I've never given a numerical relativity upshot that short. So this is kind of an experiment for me as well. Numerical relativity. And what I mean by numerical relativity, just to be very clear, is that we want to solve our Einstein's equations, or if you want to look at different equations of motion for gravity in full 3+1 dimensions as a time evolution problem. Yeah, so we want to solve Einstein's equations in 3+1 dimensions, or actually high dimensions is also possible. I've done that actually for my PhD, but let's stick to our gravitational wave description. And if we do that, we usually need to use high performance computing. Okay. And the way I like to think about it, or the way I like to split it up usually, is that we first of all have quite a list of ingredients on the theoretical level that we need to develop before we can actually start implementing numerically or computationally our set of equations to then simulate, for example, a compact binary that emits gravitational waves. And also, let me just add this here, that this is done without any weak field approximation. So this is really in the strong field regime of gravity. Yeah, where nonlinear terms in Einstein's equations become important. Okay, so as I said, I think this is what I would go by. Main ingredients, both theoretical and computational. And the main parts that we have, so the theoretical ingredients, would be the following. So the very first thing that we typically do is that we take Einstein's equations, which have this really beautiful, or take our four-dimensional spacetime, which has this really beautiful structure, and split that up and make the time direction and the spatial direction explicit. So the very first thing that we would do is perform a 3+1 or space-time split of our space-time. And as I said, so I can go in a little bit more detail of that afterwards, but I think we should just first understand what do we actually have to think about if we want to do that. So after we've split our space-time, we also apply this decomposition to our field equations, to our Einstein equations.
Excuse me.
Yes?
Yeah, just one question. Is this 3+1 split just an ADM decomposition or something different?
Say again, is
it an ADM foliation or something different?
Yeah. So that's exactly the comment that I wanted to make now. So we so in numerical relativity, we call the equations that we get ADM equations, but they are in terms of three-dimensional metric and the extrinsic curvature, not in terms of the canonical momentum. But we know that they are related to each other. So it is a very similar formulation.
The choice of time is the extrinsic curvature of the spatial slice?
Yeah. Okay, so yes, someone else had a question?
I just wanted to know, like, is there a reason why you want to choose particularly the extrinsic curvature, or is it just a choice? And you can make a different choice. Like, is there a reason why it's more natural or something?
Yeah, so this is essentially the natural decomposition that you would get if you say okay, so let me maybe just write this out first, and then I go through the other steps bit by bit. Okay, so as I said, this is going to be a little bit okay, good.
I can ask later in the Q&A.
No, that's fine. But since it's probably better to explain the different concepts, I should probably start with that. And then if I don't get through completely, that's fine. So as I said, the first thing that we would do is this space-time split of our space-time. That is the foliation. Yeah, and this is really along the lines of ADM. So we foliate our four-dimensional space-time into space-like hypersurfaces. Sigma labeled usually with some t, and spatial or induced metric little gamma with some level set. parameter t. Okay, so in other words, if I call my space-time manifold curly m, let me put the 4 here so to make it different from our chirp mass, that would be foliated into the real numbers times our 3-dimensional hypersurfaces. Okay, so if I were to sketch this, we would get the following picture. So let's just have our time direction here, and then we would have our slices here. So that would be some sigma t with a metric, with a spatial metric, gamma ij. We would have a next time slice here, some sigma t plus delta t, again with its own spatial metric. And now the first thing that we need to think about is how we would propagate a point on our first hypersurface to a point, or the equivalent point on the next hypersurface. Let me call this P, and the next one here P prime, right? So this would follow some kind of line here. Now what we introduce to describe this is the following. So we will introduce a normal vector, which is time-like in mu. And then we will have, let me work a little bit with colors, we will have a function that is called the lapse function that describes essentially the time that elapses between one time slice and the next as you move along the normal, right? So this here would be the lapse function. I call it, or numerical relativity, we typically call it alpha times n mu. If you're more familiar with a ADM-like formulation, you may recognize that as what's used as capital N. And then we also have to describe the spatial shift between the point that we would arrive at if we follow the normal, or an observer who travels along the normal direction, to where our point actually sits. And this is what we call the shift vector, beta I. So again, you may be more familiar with if people use capital Ni for this. Numerical relativity, this is kind of the standard form that we use here. So let me just, write what these quantities are. So as I said, we have on our hypersurface a 3 metric, or an induced spatial metric, gamma ij, that measures lengths within this hypersurface. Yeah, so you would have some, say, dl squared line element in sigma given by gamma ij dxi dxj. Now I also introduced this normal vector, which is a time-like normal. So unit normal vector n mu, and it's normalized such that n mu equals -1. And then we just introduced the lapse function alpha, which measures the proper time between hypersurfaces as measured by an observer that moves along the normal. Let me just abbreviate this like so. Okay, and then the shift vector beta I is a relative, so it can actually also be interpreted as a relative velocity between the normal observer and the lines of constant spatial coordinates. So it's kind of a displacement or shift. Okay, good. So we can use those, so a few notes on those. So these two, lapse and shift, actually encode the coordinate degree of freedom that we have in general relativity. So they describe also our coordinates. Okay, and if we take all of those together, we can write our metric or rewrite our metric in the following form. We say our line element for the four-dimensional metric can be written, dx nu, can be written as minus lab squared minus beta I dt squared plus, and I'm assuming here symmetry, gamma ij beta I, and then we have dt dxj plus, oh, wait a second. Yeah, that's right. And then we have our spatial metric contracted with our spatial coordinates, dxi, dxj. Okay, good. One more notion, and that explains Stefano's question about the extrinsic curvature. So that's the last notion that we would need to introduce to fully describe our space-time. And that is essentially the question, if I have this hypersurface, and we are not necessarily in flat space, so this hypersurface can be curved by itself. So the next question is, how can we describe how this hypersurface is embedded into our four-dimensional manifold? And that's exactly what the extrinsic curvature describes. So this is a geometric quantity to describe the embedding of our hypersurface. So let me write that down on the next slide. So, so we would introduce the extrinsic curvature, and we call that K, well, let me write K mu nu. So if you think about it, let me just project onto one line. So if that would be our hypersurface, then we would like to understand how the normal vector onto this hypersurface is transported along our hypersurface, right? So it may be, my drawing again is not very good, but there could possibly be an angle between the original position. So the question is, how is that parallel transported? And the extrinsic curvature gives us a measure for the change of the direction of our normal vector. So you would introduce the extrinsic curvature K mu nu as, I'm using sign convention here, minus sign, so that our normal vector is future directed. And then we have here a projection operator related to the induced metric gamma nu, and here we would have essentially the derivative, covariant derivative of the normal vector n mu. Yeah. So, and the reason, or maybe, so I don't know whether that is the reason why in numerical relativity we use extrinsic curvature, but it's a really nice geometric interpretation of this quantity. And you can show, so if you do the calculation carefully, you can actually show that this can be related to minus 1/2 alpha times the time derivative minus some Lie derivative along the shift of our spatial metric. And let me use four-dimensional indices in adapted coordinates. Both the three-metric and extrinsic curvature would just be spatial quantities. Yeah, and this gives us already the first evolution equation to describe our space-time. So this is essentially describing the kinematics. So if you were to think about classical mechanics, that would be like, the time derivative of your position equals velocity. Yeah. So
Helvi, is there a natural break point or?
Yeah, so I would break here. I just, because we had these questions, I thought it's better to explain
Sure.
this, and then I think we can break here because, conceptually, one would now apply the same kind of split to Einstein's equations. And if you're interested, I can talk about that for 5 minutes in the question and answer session, just to identify what type of equations do we get, and then maybe stop there. So I would stop here, but then answer more questions.
Okay.
Yeah.
All right. Let's thank Helvi again.
Mm-hmm.
Thanks a lot. And yeah, if there are any quick questions, sometime. And I guess, questions on this might be better suited to the discussion, because you're going to continue that anyway. So, but any immediate questions?
Yeah, I should also say, so for those of you who are interested, that we are organizing this Einstein Toolkit School at UIUC, all online, in the end of July. So I've put the link for that into the wiki. And there, on the very first day, I will give a 1 hour and a half lecture on these basic concepts in numerical relativity. So if you don't finish that now, you can just register and join us there. The registration is for free. We just need to know, how many people are coming. And then if you want to get some hands-on experience on a numerical relativity code and how to do simulations, you're very welcome to join us for the school.
Okay. Are there any more immediate questions? Okay, if not, let's sort of break, and then we'll come back and see how to approach it. But yeah,
after the fact.
Okay, good. So yeah, thanks again for letting me finish this part. And what we started talking about is, in very conceptual terms, how we would actually go about simulating a compact binary, say 2 black holes, during their late inspire and merger using numerical relativity methods. So for those of you who weren't in my lecture, I essentially started describing very briefly the decomposition of a 4-dimensional space-time into spatial 3-dimensional hypersurfaces labeled by a time parameter, and then that comes with a spatial metric that we call gamma mu nu. And to fully describe our space-time, we need the second object here that we call the extrinsic curvature. That is really a measure of how the normal vector to the hypersurface would change as you parallel transport it across the surface. And that already gives us a first evolution equation that is a kinematic equation for the 3 metric, for the spatial metric gamma mu nu here. And this is what we stopped with when I finished my lecture. Now, just to give you a very brief taste, the next step that we would do theoretically still to derive a set of evolution equations is actually applying this 3+1 decomposition to our field equations. So some of you may be more familiar with the term ADM decomposition, and that's very closely related. So in the ADM formulation, you would have canonical momenta. We typically use this extrinsic curvature, which is a geometric quantity well adapted to our space-time. The next step that we would want to do, and again, I will not go into any details here, just give you the final result. So if you perform this 3+1 split of the field equations, you would essentially arrive at 2 sets of equations. So the first set of equations would be a set of constraints. In particular, you would get the Hamiltonian constraint, which is actually related to the Hamiltonian that you have in the ADM formulation. And this is nothing else at least in vacuum, the Ricci scalar in 3 dimensions, plus or minus this particular combination of the extrinsic curvature equals to 0. And the second one is what we call the momentum constraint. And this can be written as and is given essentially by the divergence of our extrinsic curvature. So here we would have the spatial covariant derivative Kij minus covariant derivative of the trace of the extrinsic curvature equals to 0. And these equations, typically, we would solve only for the initial configuration of our system, for the initial data. So we solve these under certain assumptions for initial data. That is for the 3-metric and extrinsic curvature at t equals 0. So this is what we would prepare on our initial time slice. Now the second set of equations are evolution or hyperbolic type equations. And again, there's this one part that we've already seen. So the kinematic equation, let me just write it down for completeness, would be the time derivative of our 3-metric is given by -2 times the Lebesgue function times extrinsic curvature plus this Lie derivative along the shift vector here. Okay. The split of our field equation would also give us a dynamical equation. So we would end up with an equation for the extrinsic curvature here, which is to leading order at least given by minus the second derivative of the Lebesgue function plus alpha times the 3 Ricci tensor plus terms of the order k squared. I'm not going to write this out here. But these two equations in principle would describe the time evolution of our metric and extrinsic curvature. So that's what, well, that's not exactly what we would implement. So we still would have to work a little bit harder to get a system of equations that actually is it's a well, mathematically well-posed initial value formulation, but I don't think I have time and or will go into that here at all. Okay, so that's the second ingredient. And just as a side note, maybe, well, we need to rewrite it as a well-posed initial value formulation, but in general relativity, we actually know how to do this. Okay, good. So again, just very sketchy. The next ingredient that we would need, and remember when I actually started talking about this in the end of my lecture, I just said I actually would just give you kind of a list of ingredients that we need to put all together to then be able to implement a numerical relativity code that's able to simulate compact binaries. So the next question would be about choosing a gauge. And maybe just as a highlight, so this essentially means we need to make a choice for the Lebesgue function and the shift vector. And you might say, well, this is a gauge. We can choose anything that we want. Why don't we just choose the Lebesgue to be 1 and the shift to be 0? That's the simplest thing we could possibly think of. Why don't we do this? Do you have any ideas?
It could ruin the well-posedness, because the well-posedness only works for certain gauges, as far as I understand.
Okay, that's a good point. That's not the main reason, but yes, we do have to think very carefully about which gauge we choose to accomplish well-post initial value formulation. But there's actually a much simpler issue. So if you were to choose your labs to be 1 and your shift to be 0, that means that your observers are traveling along the normal. As you may know from your basic general relativity course, these observers, these geodesics along the normal, would actually all end up in the black hole singularity, inevitably. So if we, with the simplest choice, we would always eventually reach the black hole physical singularity, and then our code would crash. So our code cannot deal with singularities or infinities. So that's why we have to work a little bit harder to think about choices for the labs and the shift that will help us avoid the black hole singularity. And that's actually what we do. So maybe just as a note, yeah, so simplest here is not always the best. And in fact, so if you choose alpha equals 1, beta equals 0, we reach the singularity in a finite time. Yeah, so what we do instead in practice is finding a set of hyperbolic, that is evolution equations for the labs and shift. And in particular, we choose them in such a way, or at least a large group of codes chooses it in such a way that the labs goes to 0 close to the singularity. So we essentially end up with a slicing with a foliation that really avoids the physical singularity. And the shift is so chosen in such a way that it, so it's also a time evolution equation that allows us to reduce any shears in the coordinates that may come about due to, for example, 2 objects orbiting around each other. So this will lead to deformation of the space-time, and the way we choose the shift evolution equation is counteracting that so that we don't get too strong gradients, so that everything still behaves nicely numerically. And again, I'm not going to go into any of the details here. Okay, so this gauge choice, a little bit how we do treat singularities. Maybe the final item, and this really is more like if you want to read up on this, more like a reading list. So the final items, so what we actually want to get out of these simulations are physical observables. And in particular, we want to compute, for example, our gravitational wave signal emitted by this inspiraling and merging compact binary. So the physical observables would be, for example, so gravitational wave emission, and we use here actually usually the Newman-Penrose or Weil scalars. So I know that these are in principle introduced when you look at perturbations around Kerr. So we use these quantities that are well defined far away from the source, and we compute them in the far field region to get information about the gravitational radiation. So. Yeah, and if you're familiar with the formalism, then it's in the right frame. It's psi 4 that indicates outgoing gravitational radiation. And as local concept, or to understand and measure locally the properties of our individual or final black holes, we would look at a concept called apparent horizon. And this is a local in time concept that we can, so it's essentially the marginally trapped outermost surface that we can measure on each time slice in our evolution. So unlike the event horizon, where you have to know the entire space-time, the parent horizon allows us, or we can compute the parent horizon at each time step individually. Okay, so, and then once you do all of this calculation, you will find this really nice, not just illustration, but information about the strong field regime that's encoded in the gravitational wave signal that we have drawn and seen in our previous lecture. And now I think I will really stop in the interest of time, and you know, anyone who wants to ask more detailed questions, because I know this was like really a super short crash course in just what kind of quantities we need, you can ask me questions either now or in the breakout room. But I think I would also like to give Monica time to, you know, interact with you. So I would stop here and thank you very much.
Thanks a lot, Helvi. Okay, I suggest, in the interest of time, that we just break out now, unless there's really quick questions. If anyone wants to, I guess I should always allow for that. But yeah, let's break out. So I'm going to make 2 breakout rooms, and Helvi, can you? So